All right, let's dive into something from computer science that honestly feels like it should be totally impossible. Imagine this. You write a program, you run it, and what does it do? It prints out a perfect character-for-character copy of its own source code. Seriously, no tricks. It's not cheating by reading its own file. It just somehow replicates itself. So where does an idea like this even begin? Well, it actually starts with this totally bizarre sentence right here. This is a famous paradox from the philosopher Willard Van Orman Quine. It's a real mind-bender, right? A loop of self-reference that kind of sets the stage for doing the exact same thing, but with code. And that brings us to the actual definition. A quine, as it's called, is a computer program that takes zero input, nothing at all, and produces a copy of its own source code as its only output. Yep, a program that prints itself. And that name, Quine, well, it was coined by Douglas Hofstadter in his legendary book, Gödel, Escher, Bach, as a shout-out to the very philosopher who got everyone thinking about this stuff. Okay, I know what you're probably thinking. No way, that can't be real. Well, feast your eyes on this. Up top, you've got the source code for a Java program, and right below it, that's what the program spits out when you run it. They are 100% identical, down to the last character. This is a real working quine. It's a thing. So here's how we're going to break this down. First, we'll look at a program that prints itself. Then, we'll uncover the secret to self-replication. We'll also go over the rules of the game, because there are rules. After that, we'll see quines taken to a whole new level. And finally, look at what lies beyond the quine. All right, first up, a program that prints itself. So how in the world did we get from a tricky philosophical paradox to actual running code? Well, the idea of self-replication has actually been floating around for a surprisingly long time. The story really kicks off back in the 1940s with the genius mathematician John von Neumann. He was the first to really theorize about self-reproducing machines. Fast forward to the 1960s, and a researcher named Hamish Dewar actually made it happen. He wrote the first ever self-reproducing program. And then, in '79, Douglas Hofstadter came along and gave it that cool name we all use today, the quine. Which, of course, brings us to the million-dollar question, how is this even possible? How can a piece of code contain a complete blueprint of itself and also have the engine to print that blueprint? The secret is this really clever two-part structure. Think of it like this. Part one is the blueprint. This is just a piece of data, usually a string, that holds the source code for the other part of the program. Part two is the engine. This is the actual code that runs. And the engine's job is surprisingly simple. First, it prints out the code part, using the blueprint data. And then it prints out the data part, the blueprint itself. When you put those two pieces of output together, boom, you get a perfect copy of the whole program. It's a beautiful little trick. But here's where it gets really interesting. There are rules to this game. You can't just do it any old way. To be a true Queenie, you have to achieve this self-replication with a bit of elegance. You know, no cheating. So what's considered cheating? Well, the biggest no-no is reading your own source code file. That's just too easy, right? Also, an empty program that prints nothing? Yeah, that doesn't count. Clever, but nope. It also can't rely on weird compiler errors to print its code or use some language quirk where typing a single number just automatically prints that number. The whole point is that the program has to genuinely generate its own code from its own internal logic. And this little shell script is a perfect example of what not to do. It looks like a quine, but it's a total cheater. All it does is use the cat command to literally print its own file. I mean, sure, it works, but it breaks the golden rule. No reading your own source file. It's a neat trick, but definitely not a real quine. Okay, so once programmers figured out the basic recipe, you know what happened next, right? They started asking, how far can we push this? And this is where things go from clever to completely mind-blowing. First up, we have the Ouroboros program. And yes, it's named after that ancient symbol of a snake eating its own tail, which is just a perfect metaphor. Because instead of one program printing itself, you have a program in, say, language A that prints the source code for a totally different program in language B. And that program, when you run it, prints the original program in language A, completing this amazing cycle. So let's picture it. You start with a program written in Haskell. When you run it, it doesn't print itself. Nope, it prints the source code for a completely different program, this time in Python.
And when you run that Python program, it prints the code for a program in Ruby. And then, to close the loop, the Ruby program prints out the original Haskell code. Back to where we started. How cool is that?
Now, if you think a three-language loop is impressive, get ready for this. It gets so much wilder. A programmer named Yusuke Endo created an Ouroboros program with a cycle of, wait for it, 128 different programming languages. I mean, that's just a monumental feat of coding artistry. Absolutely incredible. Now, it's really important not to get this confused with a couple of other related but different cool ideas. First, you have the multi-Quine. This is a whole set of programs, and any one of them can print any of the others, or even itself, depending on what you tell it to do. Then there's the polyglot, which is maybe even weirder. That's a single piece of source code that is somehow a valid program in multiple languages at the same time. Both are super fascinating, but they're not the same as that circular Ouroboros chain. Okay, but if you thought that was complex, you might want to sit down for this one. This is called a radiation-hardened Quine, and it is exactly as cool as it sounds. It's a program so ridiculously resilient that you can literally delete any single character from its source code, run the broken version, and it still prints out the original, complete, perfect program. It's not just self-replicating, it's self-repairing. Just wow. All right, to wrap things up, let's look at one last idea. This one takes the concept of self-reference out of the world of running programs and into the world of plain old static data. And this is the hash Quine. You could basically think of it as the Quine's cousin, but for data. So every file has a unique digital fingerprint, right? We call it a hash. A hash Quine is a file, it can be a PDF, an image, whatever, that has been painstakingly engineered to contain its own digital fingerprint. So if you run a hash calculation on the file, the string of characters you get back is already sitting right there inside the file itself. And that's the key difference you gotta remember. A Quine is a program. It executes, it runs, it generates its own code. A hash Quine is just a static file. It just is. It doesn't do anything. It's more of a mathematical curiosity, a point where the data and its own signature become one and the same. It's basically the data version of a sentence that perfectly describes itself. So from a philosopher's weird sentence all the way to self-repairing code, the Quine is so much more than just a neat programming trick. It really makes you think about the nature of information itself, about replication. I mean, if we can create a program that contains both the blueprint for its own existence and the engine to build itself, what does that say about other, far more complex replicating systems, like life? It's a mind-bending question, isn't it? One that really blurs the line between code and creation.